This recording started. We are recording, audio and videos up. We are live. Welcome to Statics. Today is a very important lecture in the class. We introduce one of the most important topics today in statics, which is the concept of a moment about a point, which we're going to be using, basically from here on out. Some housekeeping items before we get started. I didn't want to take up too much time in class to talk about the exam, but I will say a couple things. If you go to Microsoft Teams for the class, you're going to see a video on the Teams channel where I talk about the exam. I go through the statistics for how the class did on the exam. You all did very well as a class. I go through some suggestions for some future exams and just some other little housekeeping items. I also sent everybody in the class a PDF detailed report which shows, how you did on the exam. It shows what was deducted and why. So between that and what was posted on Teams, you should have a really good idea of how the exam went. And again, I think everybody did very, very well. The attendance grades are up to date. Homework 3.1, the cross product homework is due today, and I'm going to assign a homework 3.2, which is using cross products to determine moments. So with that, I want to jump right into it, and I want to begin by recalling cross products and making sure that everybody remembers how to do that. So let's make sure that we remember what a cross product is. A cross product is when you take vector 1 and vector 2 and multiply them in such a way that you get vector 3. Okay. Now, vector 3 has to have certain properties in order to be defined as a cross product. Those properties are in relation to its magnitude. The magnitude of that cross product must be equal to the area of the parallelogram formed by A and B, and you'll kind of see today where that's relevant for statics when we talk about moments. And the direction. So the magnitude has to be the area, the direction has to be normal to the plane containing those two vectors. And that'll make sense even from a physics standpoint when we talk about moments and how that's related. Now, the formula for a cross product is the yellow formula that you see on the upper right. So A cross B, you form a 3x3 matrix. The top row is IJK. The middle row is the coefficients of your first vector, and the bottom row is the coefficients of your second vector. And then the cross product is the determinant of that matrix. Now, there's a number of ways to determine that determinant, to evaluate it. You could just plug it into your Casio. Your Casio will do that. I think that can be a bit cumbersome, but you can do that. That's one. But really, I found the two go-to methods to do it by hand are either the rule of Saris, where you write those two columns over again and take all your products down and to the right as positive and down and to the left as negative. That's one way of doing it. And the other way is cofactor expansion. I'm actually going to use cofactor expansion on Monday to explain moments in 2D because the formula simplifies quite a bit. So with that, hopefully cross products are straightforward. I mean, you had the homework assignment 3.1 on that. I know it's been a while since we talked about that, but I don't want the mechanics of computing a cross product to be very difficult. I mean, it's new, but ultimately it's not very difficult. There's just a pattern that you follow to get a cross product. Today, I want to talk about why we care about cross products, why we even considered that. And so I want, and the reason why this is important is because this is going to begin our next really big unit in the class, which is the introduction to rigid bodies. Up until now, what we've been doing is valuable, and there are real practical uses for considering situations where forces meet at a common point. One very realistic example for the civil engineers in the room is when you analyze trusses. Trusses are, I think just about everybody in here knows what a roof truss is. You have your house and you have the triangular arrangement of wooden elements that form your roof system. That's a truss. And so when you analyze trusses, each of the joints where all those members meet, each of the joints are essentially a statics of particles problem. You have all the forces meeting at a common point. And so that has a very real application. But the vast majority of problems that we deal with as engineers deal with issues where the forces aren't meeting a common point. And so we need to understand how to assess non-concurrent force systems. And so that's kind of the point of this. And so I want to talk about rigid bodies. And I need to introduce a couple of ideas, the big one being moments. I also need to talk about the principle of transmissibility. But before we get into like the math and the equations and the theory, I want to keep it simple, okay? And so I thought of these two problems because they're kind of related, and I want to illustrate what's going on and why this stuff matters and what's the themes. So let's take these two problems. So let's take the problem on the left first, okay? So the problem on the left is, let's say we have a Jenga tower on a table, okay? And so I'm going to actually turn the camera or the share off because I want to show this on the camera. Okay, so I have this little box here, and so let's say here's the box. Let's just say, for the sake of discussion, that this is my Jenga tower. Okay, and so if you've ever played the game of Jenga, it's a very delicate game. Maybe I'll stack this marker on top of this to kind of give me a little bit of wobbliness to it. Okay, now let's say that I issue you a challenge, and I say I want you to push this Jenga tower across the table, and it can't topple over, it can't fall apart. So you have to push it across the table, but you can only use one hand. You can't use both hands to keep it stable. You have to only use one hand to push this Jenga tower across the table. So imagine that this was a Jenga tower. I should have had a Jenga tower in class today, but I think that I would have had a big mess up in my office because I can be a clumsy guy at times. So imagine, for the sake of discussion, this is a Jenga tower and I need to push it across the table. It wouldn't make sense for me to push it along the top, because if I push it along the top, I mean, imagine there's a Jenga tower, it's just going to fall over. So if I wanted to slide it across the table, my best success is going to be if I push it and I put my hand towards the very, very bottom. Because again, if I push it towards the top, it's just going to fall over. And so just keep that thought experiment in your head, because I want that thought experiment to sort of be compared to my next one. All right, so here's my next one, once I can share these slides. Okay, so I have here a mechanic, and this mechanic is trying to loosen this this bolt on this engine component. Why is the mechanic gripping the end of the wrench and not the base? Like, why is the mechanic why? I mean, you could see the mechanic is gripping it at the very, very end. Why grip it there? Why not grip it here? Why not grip it here? More leverage. And there's a word that was sort of thrown into the chat here, which is a very careful word to throw around. The idea was that there's more torque. Okay, and so the concept of torque and the concept of a moment are very, very similar. I'll talk about the differences here in a second. But you're generally right. But let's talk about that. Let's actually see if we can define these terms, rigorously and usefully for analysis in statics. So what we have here, the common theme with these two scenarios, is that they deal with forces that are not meeting at a common point. With the Jenga tower, we wanted the Jenga tower to be stable, so when we apply our force, we wanted to keep the force close to the table because we didn't want the forces to be far apart. We didn't want the table or the Jenga tower to rotate. Whereas with the bolt and the mechanic, we want the bolt to rotate. So we took the forces and we moved them very, very far apart. And so instead of forces on a given body all meeting at a common point, they're acting along different lines of action, and so they're non-concurrent. Well, what does that mean from a physics standpoint and from a statics standpoint? Let's take a look at this situation here, okay? Let's just take a look at this, all right? Now, I just made this up. It doesn't, nothing really special about it, but I have this, rigid body. We'll say it's a beam or some lever. And let's say I hold it here in my hand. If you pull up the camera, you can see I've got a little beam in my hand right here. And let's say that I put 20 pounds going down on one side of the beam, and then on the other side of the beam, 20 pounds going up. Now, if we look at this from an equations of statics standpoint, at least the equations of statics that we've investigated so far, we have in 2 dimensions, we so far have developed two equations of equilibrium, sum of forces in the x direction and sum of forces in the y direction. And if I look at that system, this system satisfies those equations, right? I've got 20 pounds going up and I got 20 pounds going down. So net positive, or the net forces in the y direction are 0, and there's no forces in the x direction are applied. So both of those equations are satisfied. But if you look at that system, I mean, ask yourself, is that system in equilibrium? The answer is no, because if you have this system and you put forces going down and forces going up like that, the system is just going to turn. It's going to spin. It's kind of like if I had a fidget spinner. How would you handle that fidget spinner? You'd grip it in the center and you spin it, right? And so to handle this, we introduce a new term. So, and by introducing this term, I kind of want to redefine what a force is. And so these definitions, these are sort of my simple way of expressing what these terms are. So one way of defining a force might be an action on a body that increases its tendency to translate. So I have an object, and if I apply a force to it, that increases its tendency to move left or right, or move up and down, or move. That's what I mean by translate, to just move. But that's an action that increases a body's tendency to translate. What about an action on a body that increases its tendency to rotate? Okay, and so we have a term for that in statics, and we call that term a moment. Okay, now somebody in the chat threw out the term torque. Moment and torque are very, very similar. In fact, they're computed using the same methodology. The difference is usually when we refer to torque, the idea with torque is that we intend to move the system, like we intend it to undergo motion. But with moment, we don't. Like, if we're talking about a bridge beam, that beam will be subjected to forces and moments, but we don't want it to move. We want it to sit still. So hence, this is statics. That's why we're using the term moment. Now, let's talk about the formal definition of a moment. Let's talk about this from a mathematics perspective. So when we talk about moment generated about a given point. And so the formula for that is a cross product, okay? And so the way that we express that is the term R cross F, okay? And R is what's termed a position vector, and it's a position, and I have here a definition for the position vector where it's the distance between the moment that, or the point that about which we are taking moments, measured to the point where F is applied. So, for example, if I have, let's say, here's a point, let's call it point A, and I want to sum moments about, or I want to determine a moment about point A, and I have a force here. So let's say I've got some force out in space, and I want to determine the moment about point A generated by this force. What I'll do is I will determine this vector R, which is measured from point A to this force F, and then the moment would just be R cross F, okay? That's going to be our definition of moment. Now, I'll go ahead and tell you that we're going to come up here in a second with a little bit of an improved definition for R. So, this definition works, but I got another definition that's going to work a little bit better. So just bear with me on that, but you'll see that here in a second. Now, let me pull the slides back up. Okay. Now, remember the whole concept of the parallelogram. Remember that the cross product, that the magnitude of that cross product is, with cross products, it's the magnitude of the first vector times the magnitude of the second vector times the sine of that angle. And so the way that we can express that is through the term F times D being the moment arm. If there's if that's a complicated term, let me explain what let me say this. I'm going to explain here in a second what the moment arm means. It's actually a lot simpler than you think, and it makes sense from a physics standpoint. But suffice it that the moment arm is sort of the shortest distance between the force and the point about which you're summing moments, or the point about which you're taking your moment. let me skip a couple of slides down the line, and we'll delve into this a bit further. I want to talk now about the principle of transmissibility. Okay, now this is something that I actually kind of skipped earlier in the semester. If you open your textbook right now and you go to chapter 1, the very first chapter, okay, and you read that chapter, you're going to find that the book says at the very beginning, it says there are 6 ideas, 6 principles by which this entire class is based upon. And what are those 6 principles? Well, 3 of them are Newton's 3 laws. You know, I think those are pretty foundational for what we do in here. There is the law of universal gravitation, you know, weight and mass and gravity and all of that. And what about the other 2? Well, the 5th one is the law of parallelograms, the way that we add one vector to another and how it forms a parallelogram. Think about the stuff that we did at the very beginning when we started adding vectors. We said that, you know, you take vectors and you add them in a tip-to-tail fashion, and then that's how you determine the resultant. Everything that we did with x and y components and I and j was all kind of built upon that. Okay, so those are the 5 of the 6 principles. What's the 6th? The 6th is the principle of transmissibility. So what do I mean by the principle of transmissibility? So the principle of transmissibility states that 2 forces of equal magnitude and direction are equivalent provided that they fall along the same line of action. And so the way that I sort of explain this from a real world standpoint is to think about a tug of war. So let's say I've got a bunch of folks and they're all playing tug of war, okay? So I've got this blue team and this like purple team, okay? And so the blue team is sort of pulling towards the screen and the purple team is pulling away from the screen. Assuming that the deformation of the rope doesn't really matter that much, you can look at this image, and I'm guessing just by looking at it that this team, I mean, how far apart do you think they are? Like if I looked at this distance here, how far apart would that be? I don't know, maybe 10 feet, 15 feet? I mean, would it really matter if those 2 teams were 20 feet away or 5 feet away or 6 feet away or 16 feet away? Not really, because in the end you have the blue team pulling in one direction and the purple team pulling in another direction. Then the tug of war isn't about how far apart the teams are from another. It's about whether or not one team has more force than another. And so the idea is that as long as that force extends upon a given line of action, as long as it lies upon that same line of action, the forces are equivalent. Let's talk about what I mean by the real world. So if you remember in vector land, we can treat vectors as objects and we can add them in this tip-to-tail fashion. So almost think of a vector as a physical object. Like, for example, let's say I have a vector like this. Let's say this is my force vector, okay? And my force vector acts along this line of action. Well, with respect to a rigid body, let's say that this is the force. I can take that force and I can actually move it anywhere along this line of action. It really doesn't matter. As long as I keep it on that line of action, I can take that force and move it here. I can move it here. I can move it here. But here, it doesn't matter. Okay. Why is that relevant? Well, here's my point A. What that means is this. Here's my point A. I could actually write an R vector like this. I could write an R vector like this. I could write an R vector like this. I could write an R vector like this. Any one of those R vectors, if I take R cross F, as long as F doesn't change in magnitude and as long as F stays on this line of action, all of these, like R1 cross F, R2 cross F, R3 cross F, and so on, as long as R points to the same line, you will get the same answer for all of these moments. And the reason why is because what we really care about is this. We have our force. Let me sort of rewrite this. Okay, so here's my force. Here's my point out in space. What I really care about is this. I care about the magnitude of that force, and I really care about this distance here. This is the shortest distance between the point and my line of action. So we'll call this the shortest distance between point of interest and the line of action. And we have another name for that, that distance. The shortest distance between the point of interest and the line of action is called the moment arm. See, I'll show, I have an animation that goes along with that. I'm not really the best animator here, but let me show you something. So. Okay. So yeah, so as long as your force remains along that same line of action, you can move it. Now let's go back to cross products. Remember, cross products are the area of the parallelogram formed by those two vectors. Well, one of the things about geometry is that if you look at the parallelogram, the formula for the area of a parallelogram, it's just the base times the height. So if you look on this slide, you could see how the parallelogram is sort of like, see how it's sort of shifting along that line? Well, as it shifts along that line, the green area, the area of that parallelogram, it stays the same, okay? The area doesn't change. This is one of the reasons why the moment is defined as R cross F and not the other way around, because F is the base of the parallelogram. We don't want that to change because it's, you know, again, the same force vector, you know, at some moment arm, okay? But as the position vector, you know, shifts along that line, as long as it goes from point A to that line of action, you will get the same area of the parallelogram, and you'll get the same moment. So a better definition from R would be that R is your position vector. R starts at the point about which you're taking a moment, and it ends at any point along the line of action. And again, I think, you know, it makes sense from a physical standpoint as well, because what you care about is that shortest distance, and you really care about that most effective moment. It's like if you have a you know, a situation like this, like I have a physical scenario here. I've got a wrench, and let's say I want to take that that nut, and I want to, you know, lefty loosey, I want to loosen that nut. Well, I would push on this this wrench right here, but what's the best way of pushing, right? Well, it's, you know, at that right angle. I want that perpendicular distance because that's going to give me the most effective turn of that wrench, you know, shortest distance, okay? Does that make sense? Good deal. All right, now here's the thing that I always think is interesting is I promise you that R cross F works for any R as long as R falls along that line of action. And you're thinking, oh, come on, there's no way that works. Well, I promise you it actually does, and I want to illustrate that to you with this example. So we're actually going to start with 3D moments in here, and then we're going to simplify it later. I want to sort of do that part later. Okay, so I have this bracket that's being supported on the wall, and the actual support conditions and all that stuff doesn't really matter. We're just starting at basics here. And so I've got it that it's supported by these brackets and this like cable going from C to D. Now I know that the tension in that wire is 200 newtons. And so what I want to do is I want to determine the moment about A generated by that wire. So we're summing, so we're taking a moment about point A. So the force is this 200 newtons. So I need a vector that describes the 200 Newton force. That'll be my force vector. And then I need a position vector. Now the position vector has to start at A and it has to go to the line of action of that force. So what I'm going to do is I'm actually going to do this twice. I'm going to do this once from point A to C, because that would go to the line of action. And then I'm going to go from A to D, because that would go to the line of action as well. When it's all said and done, you will get the same answer. Now, a little bit on notation. If you have a position vector from A to C, we actually call it, we use this term here, C/A. We call this one, if it goes from A to D, we call it D/A. There's a reason for that, because there's actually a really easy way to compute position vectors, and I'm going to show you that here in a second. So with that, let me go to my notebook and let's do some math here. So let me stop this. Okay, so let me take my keyboard off here. Let me see if I can lay this down. Okay, so I want to show you on this problem here how we can use this R cross F definition with two different position vectors, and we end up getting the same answer. Now, before we start doing all this, I want to start back to super basics. And so first thing I want to do is come up with some point coordinates. And we'll keep everything in millimeters. I know that this image is in meters, and this one is in millimeters. But we'll focus on the left one for now. Okay. Now, this right here, this is the origin. Okay. And this is the y-axis. This is the z-axis. And this right here, that's the x-axis. Okay. So what I want to do is I want to see if I can start determining coordinates for each of these points. And so we're going to do this one at a time. Let's start off with point A. I'll do point A, and then I'll see if you all can do the others for me. Okay, so let's do point A. I propose that the coordinates for point A along the x-axis is 0, the y-axis is 0, and along the z-axis, it's 80 plus 240, so 320. Okay? All right. Now, what I want you all to do is, let's do the others. Let's do point B, point C, and point D. Somebody do point B first. I'll go ahead and tell you, we won't use point B, but it won't matter. I just want to get the practice out of the way to make sure that we're comfortable determining this. Somebody give me the coordinates for point B. 0, 0, 80. That's correct. How about point C? I'm going to clean that up. That looks a little weird. 0, 0, 80. Let's do point C. 300. Is that 30 or 300? 300, 0, 400. Okay. And point D. 0, 240, 80. That's exactly right. Okay, perfect. All right. Now, I want to show you something, because this is actually pretty slick. Okay, so let's determine some position vectors. Now, watch this. If you want to determine, let's say, vector AC, okay, one of the ways that we write this, the vector from A to C, a super easy way that you can do it is to take all of the C coordinates and subtract the A coordinates. I'm actually going to do this vertically. So we have C, which is 300, 0, 400, and then we have A, which is 0, 0, 320. Okay, and so if you subtract these, what you're going to get is you're going to get 80, sorry, no, I skipped ahead. 300, 0, and 80. So I propose that that vector is 300i plus 0j plus 80k. And maybe what I'll do is I'll put in millimeters. And so that's a really easy way of determining like your vector AC. Because think about how that follows. Like look at this vector A to C, right? This is vector AC right here. That's AC. Okay. And so how do I do that? Well, I go positive in the X, I go 300. In the Y, I don't change any in the Y. And in the Z direction, I go positive and I go 80. But this is another systematic way of doing it. And so if you want to go from A to C, take the coordinates of C minus the coordinates of A. So that's why the notation is this way, 2C from A. So does that make sense? All right. Now, one of the things I'm going to do to follow along this, I'm actually going to put this vector on the board because this is one of our first position vectors. So again, we are determining our cross products, R cross F, and so RCA is 300I plus 0J plus 80K. That is a vector from A to our line of action because our line of action is CD, okay? And so that vector works, okay? Let's do another one. Let's do vector AD, okay? And so this would be vector DA. Okay, and so same process. D is 0, 240, 80, and then A 0, 0, 320. And so we have 0, 240 is 240, and then 80 minus 320 is negative 240. And so AD is the position vector from D to A, which is 0I plus 240J minus 240K. Again, in millimeters. Okay, and so that one I'm going to put on the board as well. So R from D to A, which is 0I plus 240J minus 240K. Okay. Everybody with me so far? Okay. All right. Now we need to do the force vector. So I can form the force vector, or at least the distance vector easily, but there's a little bit more going on with the force vector. But nothing that I'm doing here is any different than what we've really done in the past. So let's do the force vector. Okay. So first off, we have the force vector, but we know the magnitude of that force is 200. What was the units? Was it newtons? Yeah, newtons. Couldn't remember if it was newtons or kilonewtons. Okay, so we have a 200 Newton force vector, so we know the magnitude. Now, how do we know? What about the direction? Well, we know it goes from C to D. So if I want to determine the CD vector, again, I do what I just did. I could say D, 0, 2, 40, 80, and then C, what were the coordinates of C? 300, 0, 400. All right, I need to subtract this out. So 0 minus 300 is negative 300. This is positive 240, and this is negative 320. So CD is negative 300I plus 240J minus 320K. Okay, now here's the thing. Just like the other vectors, all of these numbers, the 300, the 240, the 320, this is in millimeters. That is not a force vector, that is a distance vector. Now let's see if you all remember this. How do we turn this from a distance vector into a force vector? Well, the first thing we have to do is we have to determine, oh goodness, that went far. The first thing that we have to do is we have to turn this into a unit vector, okay? So we need the magnitude of vector CD, which is CDX squared plus CDY squared plus CDZ squared. So we get negative 300 squared plus 240 squared plus negative 320 squared. What is that? What is the square root of all that? Tell me what you get here. I'm gonna get y'all fired up. Make sure y'all are engaged. Somebody help me out here. 500. There we go. 500, and this is millimeters, right? So therefore, I can determine a unit vector, which is the following. Okay, and so lambda CD is, okay, so 300 over 500, that's minus 0.6 plus, okay, 240 over 500, that's 0.48, and then minus 320 over 500, that's minus 0.64. And this is a unit vector, okay? So we've divided out the millimeters. This is unitless, okay? So now I can determine my force vector by taking my magnitude times lambda. So that's going to be 200 times my unit vector. So let me write that out a little bit. And so we get our force vector is, so 200 times 0.6, that's minus 120. And then we get plus 200 times 0.48 is 96. And then minus, that times that is 128. And this is going to be in newtons. So now we have a force vector. Let me write that up here. So minus 120 I plus 96J minus 128K. Okay. So just to recap and make sure that everybody's on the same page. So I've got a force vector here. That's the force from that cable. And then I have two position vectors. Both of these position vectors start at the same point and they end on the same line of action of this force. And so I propose that R cross F will give the same answer for both position vectors. And if you don't believe me, let's test it out. So let's see what happens if you take this cross this and then this cross this. You will get the same answer. Promise. So let's test that out. Like I don't know, Dr. Mike, that's a tall order. Well, let's see. Let's see what happens. All right. And so okay. So we have RCA is 300I, 0J, 80K. R DA is 0I plus 240J, and then minus 240K. And then our force vector is minus 120I plus 96 minus 128. Let's see what happens. All right, so let's do the first one. So R cross F equals, okay? And so remember, again, R is the position vector from A to the line of action. And so we do that one first. So R cross F. And then remember how we set this up. We do I, J, K. And then whenever you're doing a cross product, so R cross F, the coefficients of the first vector go in the middle row. And then the coefficients of the second vector go in the second row. All right. Now, here's the thing. I don't really care which method that you use. Some of you are probably going to like the Saris rule. Some of you are going to like cofactor expansion. I'm going to use cofactor expansion because I kind of use it on Monday for a derivation. So, but it doesn't really matter. You can use either one. Okay. So 0, 96, 80, minus 128, I, minus, and then 300, minus 120, 80, minus 128, J, plus 300, minus 120, 0, 96, K. Okay. All right. And so remember, what you do, you cover the row and the column for each of those components, and you just write the 2 by 2 for what's left over. And remember, if you have A, B, C, D, it's just A, D minus B, C, so just that minus that. So let's take each of these one at a time. So we're going to have on this one, so we're going to have 0 times 128, that's 0, minus 80 times 96. What is 80 times 96? So 80 times 96 is 7680, and that's negative because it goes the other way. So minus 7680. I, and then minus, so what do we get here? So this one's going to be a lot. So 300 times 128, that's negative 38,400. And then minus that, but it's already negative, so it's positive. And so 80 times 120, 9,600. J plus And so we get 300 times 96, 28,880. And then the other is 0 because it goes the other way. So that's 0. And so therefore, R cross F is minus 7680I. And then what do we get here? So we get a negative term inside the parentheses, but then that's negative, so that's positive. And then 38,400, 28,800. Did I do that right? Did I miss something up? Am I getting a second on that? How'd I do? All right. Good. Now let's do the other one. Let's see if we get the same answer. Okay. So R dA cross F equals. Okay, and so it's a different R vector this time. So now it's 0, 240 minus 240. And then it's negative 120, 96, 128. And so I'm going to use cofactor expansion again. So what do we get? We get that's our I, and then J all right. So this one we got 240 times 128. So negative 30720, and then minus, but then that's a negative. So 240 times 96 plus 23040 I minus. Okay, so and the first one's 0, but then we got a negative here. So 240 times 120. So positive 28,800 J, and then plus, 0, and then we have minus, but then a negative, and it's again 240 times 120. So, wait. Oh, I have a typo. That one here is minus 128. Yeah, that one, yeah. That one's right there. Yeah, that was it. Okay. And then this is 0. That is minus 28, or sorry, that's positive 28,800K. So, and then add those two up. And you get negative 7680I plus, let's see. Oh, this is negative. Wait, I've got a sign here messed up. Yeah, that's negative. That's the problem. That one's negative. So this is negative. So that makes that positive. 28,800 J plus 288K. So they work. Same answers either way. So our moment, which is a vector, so we'll say moment about point A, is minus 7680I plus 28800J plus 28880K. And then the units are newtons times millimeters. Again, going back to that torque, like whenever you have a moment, the units are force times distance, kind of like a foot-pounds. So yeah. And so yeah, you get the same answer either way. Pretty neat, huh? That you use two completely different position vectors, but because they both point to the line of action, you get the same answer in the end. You have a homework problem that's, you don't have to do it two different ways, but I give you a force and a point about which to take moments. So you're going to determine the moment of a force generated at a point in a similar fashion. And so that's going to be due Monday. Any questions before we call it? Well, good deal. Well, everybody, I hope you have a wonderful weekend. We will see you all on Monday. And that's all I have. We'll see you.